Okay, now we're going to get into the very guts of calculus. Now that we have limits at our disposal of understanding. And so let's go back to this graph that I gave on the very first lesson. Y equals x squared. And what we are interested in is the slope of the function at this particular point. And so instead of just choosing the point 3 or something like I did before, I'm going to let that be the point x right there. There's the point x, and I'm interested in the slope right there. And recall that the slope is what you can think of by taking the tangent line at that point right there. So we're actually looking for the slope of that tangent line. So the question is, how do we do it? So here's what we're going to do. Remember, this is something we've done before. I'm going to choose another point a little bit away from it. Let's call that the point t. So this is the function x squared. So we're going to choose the point t, and then we're going to ask, what's the slope of the secant line that goes between those 2 points? So this, of course, is the point x squared, and this is the point t squared. And so if we can find the slope of this secant line between these 2 points, we'll have an approximation for what we're after here. Okay, so what is that again? The slope is going to be t squared minus x squared all over t minus x. There's the change in the y values, t squared minus x squared, and then t minus x. And then, this is where calculus begins. This is the whole idea of limit. We say, hey, we're not satisfied with this quantity for some value of t way over here. We want to take this t and we want to push it all the way into x. Notice we can't just let it be equal to x. You'd think that's what we would want if we'd want the tangent line. But as soon as we let t be equal to x, then this is a 0 and this is 0. So we have 0 over 0, which is not defined. So we can't do that, but what we can do is, in lieu of that, is to say, let's push this thing into x. Let's let it get arbitrarily close to x. And of course, that's the idea of the limit. And it took mathematicians a long time to kind of try to figure out how do we go about getting this? They had the rough idea of how to do it, but they didn't want to say that it was actually equal to x, but they didn't want it to be any finite distance away. They wanted it to be as close to x as possible. So they wanted to push it into x. So this idea of limit took a while for mathematicians to even kind of figure out exactly what it was they were wanting to do. So that's it right there. And this is such an important notion, this idea of being able to find the slope at this point, that we give this thing its own name. We call it the derivative of f at x. We put f down, f is our function, and here we have f with a little dash mark or slash mark there. We call that the derivative. It's because it's derived from the function f. And so this derivative is going to be the function that gives us the slope at any point x. I just chose any arbitrary point x here, and this thing here is going to give us the slope at x. And let's go ahead and evaluate it. So what do we get here? We get limit as t approaches x. Recall what we can do here. Break that up. And then this can divide off with this, because as long as t is not equal to x, that number is exactly the same as that. And now as t gets closer and closer and closer to x, this approaches x, this stays x, x plus x is getting closer and closer to 2x. So there's our answer. How cool is that? So recall in the very first lesson, I think I had the 0.3 here, and we found that the slope at this point was 6. And so now we're discovering the more general rule. Given any point along the parabola, if you want to know what the slope is there, the slope is just twice the value of the x value. So at 3, the value is 6. If I wanted to start at 5, the slope would be 10. If I was over here at -4, the slope would be -8. Here at 0, the slope is 0, and so on. How cool is that? I got goosebumps the first time I saw this in a calculus class. It was just the coolest thing in the world. It just got me all totally excited. I remember asking my high school teacher, does anyone else know about this? And he said, you mean in the school? And I said, no, in the world. It just seemed like it was a totally new idea that I'd never thought about before. Just fantastic. So there it is right there. Here's another way to get exactly the same answer, but to just label the points differently. Here's another way to do it. So it's still the derivative. We're still going to take the limit. But instead of labeling this point t, we're going to label it x plus h. So the reason we do that is because we think this is our point x and this is going to be just a little bit away from this one. So we take x and we add h to it. H will be a small number, and that'll either be over here if h is positive or be here if h is negative. So now the coordinates of this point are x plus h, comma, quantity x plus h squared. There's the coordinates of that point. So now what do? We do exactly the same thing as before. We take this value minus this value. So it's going to be x plus h, quantity squared. That's this y value, minus x squared. All over the change in the x values down here on the x-axis. So x plus h minus x, well, that's easy enough. X plus h minus x is just h. So there's the difference in the y values divided by the difference in the x values. We want to push this one into this one. So the way we push it into this one is by taking the limit as h goes to 0. And so we should end up with exactly the same answer, even though this looks very different at this point. Let's see what happens. So it's the limit as h goes to 0. We know how to multiply things out. If you multiply that out, you're going to get x squared plus 2xh plus h squared minus x squared, all divided by h. Then notice that that cancels with this. And now I can factor an h out of these two. All divided by h. This divides out with this. Notice that until I divided out those h's, everything here, if I would have just let this point be equal to that point, if I'd let h be 0, I would have gotten 0 over 0 again. So at all these values, all the way down here, I would have gotten 0 over 0. It's finally here when I divide out the h's that I no longer have 0 over 0, and I can still take the limit as h goes to 0. As h goes to 0, sure enough, look, this goes to 0, I get my 2x. So the same result as before. Either one of these is a perfectly good definition of the derivative. Sometimes this one's more convenient, sometimes this one. So let's now give a general definition for a derivative. If you just have any old function here, it doesn't matter what the function is, something like this, and I have a point x right there, this is the function f of x, then definition, f prime of x is defined to be the limit. We can use either one. I'm just going to write one of them down as h goes to 0 of f of x plus h minus f of x all over h. This is defined to be this. As long as this limit exists, then this is defined to be this. this thing here is called the derivative of f. Okay, there you go. So let's do a few more things. We're going to find a whole lot of other derivatives in the next lesson, but let's just learn a few things more generally here before we go on. First of all, notice that if this is the function x squared, then what did we say? The derivative of that function is 2x. And 2x, if I were to graph that on the same graph, then what does 2x look like? It's just a straight line going up like this, going down like that. That's the first derivative. I should say that's the derivative. Now, 2x is another function. That's a straight line. If I were to find what's the slope of this line at every point, that would be the derivative of this function. What is the slope of this line at every point? It's obviously 2. So we'll prove this in the next lesson, but it's clear enough that if I wanted to express the derivative of this function, well, then I want the derivative of the derivative. How do we express the derivative of the derivative? That's 2 primes there. The derivative of the derivative is in this case, what do we say? The slope at every point there is 2, which looks like this. And let's put this one down. Okay, so each one of these things is itself a function, and you can take the derivative of that one. Let's go one further yet. I guess we can. What's the derivative of this function? The derivative of this function, that is, what's the slope of this function at any point? The slope is 0, and we can check this out as well, but that's going to be the third derivative. Would be 0, because the slope of this function at any point is 0, so that would be down there. And then we could keep on taking derivatives. The derivative of 0 is 0, because this is another just constant function with no with a 0 slope the whole way. So there you go. Once you go past 3, it gets a little bit untidy to start putting more marks there. So in case you ever need more than 3, sometimes you use Roman numerals. Other times you put 4 in parentheses like that. There are various ways to do it. But in practice, you very seldom go beyond 3, at least in Calc 1. So there you go. Let me do one other thing in this lesson, and that is to tell you about a different notation which is used for this. Another notation is we can use this to stand for the derivative. The derivative of x squared with respect to x is 2x. You can write it like that. So that's another way to do it. If you wanted to take the second derivative, you write it like this. The second derivative of x squared with respect to x is 2, and so on. You also have the option, if you want to, just to write the derivative of the function f is 2x. Okay? There are advantages either way. The advantages of this is that I can, in one line, I can express what the function is and what the derivative is. The derivative of x squared is 2x. Here I need 2 lines to do it. I need to first indicate, here's one line that tells me what the function is, and then here's another line that tells me what the derivative is. So that's one advantage of this. The advantage of this one is, suppose I want the derivative, that is, I want the slope at a particular value. Let's say I want the slope at 5. Okay, let's just, for sake of argument, say that this is 5 right there. So we know that the slope there is 10. The advantage of this is that I can just say, okay, at any point x, the slope is 2x. So f prime of 5, I stick a 5 in here, is equal to 10. That's real convenient to write it like this. Here, it's just a little bit less convenient. The way you have to write it is you say the derivative of x squared with respect to x at x equal 5 is equal to 10. So a little more cumbersome, but it works fine. By the way, another way to write this, let me just make sure you see everything here. Since the y coordinate of the graph is what you get by taking the value of the function, another way of often writing this is just to say dy dx is equal to 2x. And that kind of shows why this notation was even developed. This, or something similar to this, was developed by Isaac Newton, and then Leibniz, another mathematician of the time, developed this notation. The advantage of this is, if you think about it, what we're doing over here, what did we do? We started off by asking what's the slope between these 2 points, and so that was a change of y and this was a change of x. So when we wanted the secant line, the slope of the secant line was delta y over delta x. Let me just write that down here. Delta y over delta x is the slope of the secant line. And then when you use calculus, use limits to push this one into this one, so you no longer had a big delta x, instead you pushed it all the way to 0, then Leibniz said, oh, okay, let's use something kind of similar to delta, and so he said, oh, how about d? So he just came up with this idea, dy dx is what you get by taking this, and then instead of having a finite distance there, you push it all the way in using limits, and this is the what? It's not the slope of the secant line, but it's the slope of the tangent line. Okay, so there's the definition of the derivative, and this is what we're going to be spending most of the rest of the course on, is learning more about how to find derivatives, and then more interestingly, how to actually apply them and use them in applications.